Hi Year 12s. In this video, we will derive exact values for sine, cos, and tan of very special angles 30, 45, and 60. These are values that you are expected to know by heart, or you should be able to derive them yourself from first principles without notes and without a calculator in your first exam. You'll also need to know the representations for these angles in radians, which is the unit that you will be using most of the time. To make the derivations easier to understand, I'm going to use degrees in this video until the very end, where we convert to radians. However, in future, all work that we do will be in radians for this topic. So let's start with a review of right-angled trigonometry, which is what you learned in Year 9 and 10 maths. You'll notice that there is no circle here. However, the topic is called circular functions. And the reason why is we will soon define sine, cos, and tan as coordinates on a circle. But we don't know that until Year 11. So we're still in the Year 9 and 10 world, and we're still dealing with right-angled triangles and ratios. So, to recap, suppose I give you a right-angled triangle like so, and I label one of the reference angles to be theta. So sometimes this is called the reference angle. It's a particular angle that I'm looking at, which is not the right angle, denoted by the square. And I have this restriction that the angle is between 0 and 90, otherwise it won't be a right-angled triangle. In the next video, we will relax this restriction and define sine, cos, and tan for all angles, including those beyond 90, and not just 30, 45, and 60. We label the three sides of the triangle with respect to this reference angle as follows. First, we label the hypotenuse, which is the longest side, as h. We label the side which is not touching the angle, O. And we labeled the remaining side, A, as the adjacent side. And this is the side that is touching theta, but it's not the hypotenuse. Okay, so for every angle, theta, we have O, A, and H. If I drew the angle like this, up here, then the hypotenuse would stay the same, but O and A would switch. Okay, now what does this have to do with circular functions? Well, the circular functions are sine, cos, and tan. So this is our preliminary definition, which we will soon replace. Suppose I give you an angle theta between 0 and 90. I'm going to define the sine as the ratio of the opposite side to the hypotenuse, cosine as the adjacent to the hypotenuse, and tangent as the opposite to the adjacent. Now I know I'm going over familiar territory. The reason why I'm covering this content again is because I've taught students in Year 12 methods and Year 12 physics who do not know this at the start of the year. They've forgotten it because they haven't used it. You need to have this memorized. You can't be fumbling your way through exam 1 trying to recall what sine, cos, and tan are. So if you don't know this by heart, I highly commend the SOHCAHTOA acronym, which has served generations of students well to remember this. Sine, cos, tan. Alright, with that out of the way, let's look at some exact values. So by exact value, I mean either a fraction or which may include whole numbers or square roots. So Normally, when you type in sine, cos, and tan into a calculator, you get a irrational number, which is a non-repeating decimal. Sometimes, however, we can write down very simple expressions for these trig ratios. The easiest one begins by considering a right-angled triangle, which is isosceles, with angles 1 and 1. Okay, so first question is, what are the angles in this triangle? Well, because this is an isosceles triangle, that is, these two sides are the same, we sometimes use these marks to indicate that they are the same length, and I will do that, 1 and 1. That means these two angles are the same. So the angles in the triangle add up to 180, and I've already got 90 here at the right angle. So these two angles have to add up to 90. And since they're the same, these angles are both 45 degrees. Okay, what else can we say? If we apply Pythagoras' theorem, a squared plus b squared equals c squared, where c is the length of the hypotenuse, then we can write down that the length of the hypotenuse in this particular triangle is root 2. So now that we know that, let's just consider one 45-degree angle with 1 and root 2. And I'll call this O, A, and H. What do we get? We get sine of 45 is the opposite over the hypotenuse, which is 1 over root 2. And some people prefer to write this as root 2 on 2. Cosine of 45 is the adjacent side over the hypotenuse side, which is again 1 over root 2. So we get something very interesting. Sine of 45 and cosine of 45 are the same. And tan of 45 is opposite over adjacent, which is 1 divided by 1, which is just 1. Okay, nice and easy. Root 2 on 2 for sine and cos, and 1 for tan. Now let's look at one more triangle to get exact values for 30 and 60. One thing I should say before I continue is that sine 45 is irrational because it's got root 2, but it's got a nice fraction that I can just sort of write down. If I use any other angle besides 30, 45, and 60, the expression would be much more complicated, essentially, and not as easy to write down. So we like this, and so we use it, and we expect you to know it in methods. Okay, this one is a little bit trickier. So this time what we need to do is start with an equilateral triangle. With side lengths 2. Now, you don't have to start with side lengths 2, but if you do, it's going to make the calculation easier. So, if you've forgotten, an equilateral triangle means all side lengths are the same. And what we need to do is first ask, what are the angles in this triangle? If all the sides are the same, then all the angles are the same as well. And since the angles add up to 180 degrees, if I divide that by 3, I get 60 degrees for each angle. Now, you might be asking, how does this get me to a value for 30 degrees? I don't see a right-angled triangle yet. What we need to do next is split the triangle in half. So I'll just do it like this to show you what's happening. We're going to split it down the middle like that to make a right-angled triangle. So this side is going to be 2. This is going to be the right angle. And because I split this bottom side in half, now this side length is 1. And if I use Pythagoras' theorem, the remaining side length is root 3. The angles are 60 degrees. And up here, I split the 60-degree angle in half. So now I have 30 degrees. And now we're ready to write down sine, cos, and tan for 30 and 60. So we'll start with 30 degrees. If I call this the opposite side, I call this the adjacent side, and I call this the hypotenuse side. Sine is opposite of a hypotenuse, so that gives me half. Cosine is adjacent over hypotenuse, so that gives me root 3 on 2. And tan is opposite over adjacent, which gives me 1 over root 3, which is the same as root 3 on 3. Now, if I want to consider the 60-degree angle, I need to swap O and A. So let's do that. Now I'm considering the 60-degree angle now. So now root 3 is my opposite and 1 is my adjacent side. So again, sine is opposite of our hypotenuse, so this time it's root 3 on 2. Cosine of 60 is A over H, half. And tan of 60 is O over A, root 3 on 1, which is root 3. Okay. Now, do I expect you to remember this? Well, you need to know it. You need to be able to reproduce this on your own in case you are asked to evaluate or solve equations which require you to know these values. So my suggestion is that you draw the diagram until you end up memorizing all of these results through repeated use. Don't just try to memorize it with a table. I think you'll pick this up and remember it if you use these results enough times. So if you only use it once a week, you won't remember it, but if you use it every day for 3 weeks, you'll start to remember that sine 30 is a half, and that tan 60 is root 3, and etc. But let's wrap up. So in this video, we have derived values for 30 degrees, 45 degrees, and 60 degrees. And remember that we're going to eventually work with radians. So I'll put them side by side. Remember that pi radians is 180 degrees. So dividing by 6, I get 30. Dividing by 3, I get 60. And dividing by 4, I get 45. And now we can write down sine, cos, and tan. I will do this one by memory. So you'll remember in the isosceles right-angled triangle, we had this, and we had 45 degrees. And just by looking at that triangle, I immediately know that tan of 45 degrees is 1, and sine and cos is 1 on root 2, or root 2 on 2. Similarly, if I write down the half equilateral triangle with side lengths 2, I get the following. And I tend to remember that sine of 30 is a half. And cos 60 is a half. With sine and cos swapping, and tan being larger as the angle gets larger, and root 3 is bigger than root 3 on 3. So we expect you to know this, or to be able to draw the triangles and figure it out. I prefer that students draw the triangle rather than just blindly memorizing, because if you memorize it wrong, you will do the question wrong, but if you can draw the diagram, you will be able to reproduce the correct ratio. Alright, in the next video, we will define sine, cos, and tan for other angles than 30, 45, and 60, and we will also relax the restriction that the angle is between 0 and 90. See you then.